Hello, my name is Anastasios Goyas, and I'm going to present you the main points of my project, which is Faster-than-Nyquist WDM Optical Transmission Systems. My supervisor is Professor Robert Kelly. The aim of this project, as I just said, is to investigate Faster-than-Nyquist WDM QPSK optical transmission systems. These systems are wavelength division multiplexed, which have a wavelength channel spacing less than the symbol rate, giving high information spectral density. WDM, or wavelength division multiplex systems, are used to transmit multiple channels through the same physical fiber, thus increasing the capacity of the system, as shown in the first figure. Capacity is also further increased with the use of efficient modulation techniques like QPSK or higher modulation formats, thus effectively increasing the number of bits transmitted simultaneously. QPSK is of particular importance for optical communications due to its simplicity and ease of implementation and, and its robustness to noise. Further, the use of pulse-shaping filters, such as the raised cosine and the Gaussian pulse, greatly increase performance and also the spectral efficiency. The second figure shows the raised cosine pulse. Various pulse shapes have been investigated. The raised cosine pulse, which results in the optimal square-shaped spectrum, which you can see in figure 3. Also, the Gaussian-shaped pulses have been investigated because they can be easily implemented. And lastly, modified Gaussian pulse, employing the smoothing effect between adjacent pulses, has also been analyzed and has proven to show the best results. A bit about the system, description. The emphasis was given to the implementation of an integrated system in MATLAB in order to model the end-to-end simulation of the optical WDM QPSK system, starting from the input data feed, applying all the data transformations and pulse shaping filters, channel configurations, which include carrier frequency, channel spacing, the modulation, the propagation in the fiber, the addition of additive white Gaussian noise, demodulating and decoding, the analysis and bit error rate calculation, and also the output data. Additionally, also a lot of graphs and diagrams have been implemented based on which the figures of this specific report were generated. Initially, I employed different random bit sequence generators in the WDM transmission system, so I can provide decorrelated beat sequences on neighboring channels. The data sequences are split into odd and even subsequences in order to feed the in-phase and quadrature phase components of the QPSK modulation. I then combined the generated subsequences with a pulse shaping filter to create the pulse trains. These pulse trains are then used to modulate the carriers of the separate channels of the WDM transmission system, and the results of typical pulse trains generated by the simulation are shown in the figures 4A and B. In figure 4A, we can see the pulse train corresponding to the raised cosine filter, while in figure 4B is presented the pulse train generated by the Modian Gaussian pulse filter. In terms of fiber propagation, attenuation, and dispersion, they get modeled by the transformation to the frequency domain, while nonlinearities are applied in the time domain signal. Also, additive white Gaussian noise, also known as AWGN, is modeled as a Gaussian process with a variable standard deviation. We can see in figure 5 the typical power spectrum density of an 8-channel system with a 100 gigahertz channel, as you can see with the 8 peaks. Lastly, in the simulation, the modulation is performed for every channel separately by simulating a coherent receiver, separating the in-phase and the quadrature signals, and using integration to extract the bit information. Finally, the in-phase and the quadrature bit sequences are combined to create a data sequence, which is then compared with the input sequence in order to calculate the bit error rate. In figure 6, we can see the scatterplot diagram of the in phase and quadrature signals at the receiver. The spread of the dots for this particular signal is due to the interchannel interference, as no additive white Gaussian noise was added to the system in this particular simulation. Also, a Monte Carlo mechanism is implemented for the calculation of the bit error rate. In order to achieve a close approximation to the bit error rate, I need a sufficiently large number of bits to be considered in the simulation. In the developed model, there is a direct relationship between the number of bits, the pulse duration, the sampling frequency, and the frequency spectrum that can be achieved by employing a Monte Carlo mechanism. The simulation needs to be executed multiple times with new random sequences of bits until the expected accuracy is obtained. After multiple simulations, I analyze the bit error rate versus the optical signal to noise ratio. And the results are shown on figure 7. It is clear from the results presented that the raised cosine pulse shaping exhibits the higher performance to the classical Gaussian pulse shaping due to the higher spectral efficiency. However, the modified Gaussian pulse results in even smaller bit error rate, further enhancing performance. This is due to the smoothing effect between adjacent pulses as seen in figure 4b, in contrast with the raised cosine pulse on 4a. And this results in an overall better performance. To conclude, the emphasis was on the development of an end-to-end system for the simulation of Nyquist WDM optical transmission with QPSK modulation. The effects of pulse shaping filters greatly influences the performance and efficiency of the system. I investigate the effect of a raised cosine pulse and the Gaussian pulse. And to conclude, a modified Gaussian pulse is proposed that leads to increased performance and spectral efficiency as the most efficient pulse. Thank you very much.